millionths of a second, they could discriminate between a 0 and a 1 with one of those spots you saw on the face of the tube. It was like the most amazing sort of hack, completely odd thing that they did. Yet it works. And you could have this 1,000-bit matrix, and you could go to any spot in microseconds and read whether the spot was 0 or a 1. They did that with clock cycles. And every tube had its own logbook recording its sort of illnesses and disability. But they managed to get this thing working. And so the computer ran with 40-bit words, but 1 bit was in each tube. So all 42, it wasn't like a V8 engine you can still run on 7 cylinders. This 40-cylinder engine had all 40 cylinders had to be running perfectly. When they didn't, first thing they did was take it out and hit it with a hammer because it might be a piece of dust. And then they needed input-output. We didn't have plastic tape, so they used all the recording wire, which at that time was how audio recording was done. So this is the original archetype of what now would be a hard disk or a disk drive. This is a recording wire on 2 bicycle wires. And that's a kilogram of it, that's a 40-bit word. You can see how sort of fuzzy it is and how hard it was to do million-bit calculations and everything kind of looks like that. So von Neumann was in an abstract way interested in this question of how, like any mathematical puzzle, how can you build a reliable machine using unreliable parts? That became one of the many fields that he pioneered. But the guys in the machine room, they were actually having to get this thing to work with these unreliable parts. So now we were looking at some logbooks. The question always was, when it failed, was it human or machine? So machine error, human, no use, went home. Before closing down in disgust. And all these codes are hexadecimal codes, so 40-bit hexadecimal code we still use today. But there was no operating system, no assembly language, no compiler. They just worked in raw, absolute accuracy, no floating point, nothing. Engineer gazing at tube number 36. Here they have to do a demonstration for Dr. von Neumann, so they're very nervous. And now the memory has turned to garbage, which is like an old black and white television set that just will go completely out of focus. Impossible to follow this damn thing. Where's the directory? So they're already asking me why there's no documentation for this code. Occasionally I'm just boring. So this is hardware. The drum, this is basically a head crash. But now that they've replaced the wire with the drum, the drive head is crashing the drum. There are always sort of problems. Could be human error in coding, it could be logic, it could be memory, or it could be input-output. So here the input-output people are saying it's arithmetic. It's actually logic. False start, machine or human. Maniac lost its memory, maniac regained its memory. It's always trying to find a problem in code. Code error, machine not lifting. Found trouble in code, I hope. Damn it, I can be just as stubborn as this thing. The hell with master control off, way off. Now here's a real problem. This is New Jersey in the summertime. IBM machines putting a tar-like substance on cars, and then the next country, tar is tar from roof. It's actually melting out of the roof because they could either keep the air conditioning running or the machine running. It's hard to keep both running at the same time. Here, a mouse has climbed into the blower behind the regulator rack, set blower to vibrating, result, no more mouse. And then on the tombstone, serialized mouse, question mark, died 4:50 a.m., May 27, 1052. So we know, going back to the other law, the hydrogen bomb code, this was a hydrogen bomb problem they were doing. They would run all night. And then some of the other engineers, here lies Marston mouse. And that's an inside joke because the purest of the mathematicians in Princeton was Marston Morse, who was the cousin of the Morse hardware Morse. So there were two branches of the Morse family. One stayed in Princeton and became mathematicians. The other branch moved to Bellingham and established Morse hardware. And Marston Morse was the guy who most strongly he believed in computing, but he believed it should be elsewhere. It should not be at the institute. So they're obviously making fun of Marston, like the Marston House. That's high speed, high speed was 16 kilocycles. That's low speed, which was a 2 kilocycle. So this machine did not have a fixed clock speed. It actually was asynchronous. So it would do one instruction and then go to the next. But you could sort of set like an engine, you could set the throttle. But that was very important. So when things were going wrong, you could actually slow down to one instruction at a time and look at those tubes and see what the bits were doing. But everything had to be duplicated. You couldn't trust it. So all calculations, if you're doing a hydrogen bomb problem, you do everything in pieces and you do it twice. I've now duplicated both results. How will I know which is right, assuming one result is correct? I have 2 watches and they're both wrong. This is now the 3rd different output. I know when I licked. And now we're getting later, so now we're 1958, things are really ended this project. And all troubles were code problems, which is the world we live in now. The hardware never fails, it's the software. So we had that transition, it was about 1956. We went from most of the problems being hardware problems and most of the problems being software problems. What's the use? Good night. And then over to, they weren't supposed to talk, the bombs were completely secret. This computer was actually built to do hydrogen bomb calculations. So the smoke screening was being done to do meteorology. It really being done. And that here, one of the engineers has sort of broken the rules and drawn a mushroom cloud and water. It was a tremendous success. It was the first case of something modeled in a computer having a huge effect on the real world. And that 10 megatons, 10 million tons of high explosive was the result of those calculations. Robert Oppenheimer, who sort of went to the grave being credited as having objected to the hydrogen bomb, actually he's supported this program quite strongly, so didn't really want to admit it. So as far back as this is August, this is the day we dropped the bomb on Nagasaki, August 9th. And already there's a telegram that's for Edgar Teller saying Stan and Nick can now act openly as coming from themselves. They were already there. Even before the end of the war, the mathematicians were there working on these hydrogen bomb problems. It was not like we did the hydrogen bomb in response to something else. It was all changes our view of history. Stan it's not Stan Ulam, it's Stan Frankel and Nick Metropolis. Nick Metropolis, who invented the Monte Carlo algorithm, was probably the most successful code ever invented. Here it is, Nick Metropolis, a young Greek American. All these people, most of them were foreigners who would have trouble getting visas today, but the reason America is the superpower it is because of these people who came in the 1930s and 40s. There's Nick Metropolis over here. And Stan Ulam is totally winning in poker. Los Alamos had a weekly poker game. So they invented this thing. The important thing is that they had fun. They did all this stuff, but they didn't work very hard. They worked a few hours a day and had a lot of fun. Nobody asked them what they were producing. And so Monte Carlo was sort of answering, you have these incredibly difficult physical problems that cannot be solved analytically. And Stan Ulam, who had encephalitis and was told not to do any intellectual work and just to play solitaire, he started thinking how you could solve the solitaire problem by just playing the games. And that became the Monte Carlo method of statistically solving these unsolvable problems. You solved all the bomb problems and solved them. It's still used millions of times a day. And when Neumann took that, the Princeton computer wasn't running yet, but he figured out how to get this Monte Carlo to actually run on the ENIAC, to take the ENIAC, which was not a programmable computer, and get Monte Carlo to run. This is a manuscript written with his wife, Clara, who he went back to Budapest in 1937. She was a Hungarian figure skating champion at age 14, but did very poorly in school. But he taught her to program. He needed somebody, he wanted to show that computing could be done by anybody. And so Clara was like the perfect example. So he trained her. She actually she did all the early programming for these Monte Carlo codes. And they drove away. This is V8 Cadillac. So, in 11 years, they crossed the United States 28 times, both ways, with no seatbelts, no air conditioning, no FM radio. And they wrote back and forth, they're always in different places. So for me as a historian, I found kind of they had all their correspondence. So they're writing about these Irish and Montclair. A lot of it is about their marriage, which was always breaking up, but the rest of it is about Monte Carlo. So that, to show you how small the codes are, that's a complete code for a complete hydrogen bomb code in that one envelope. There's 4 pages. So none of this, Windows XP or anything. So they have a sense of humor. This is phenomenal right every time. So they were the 2 guys who were really trying to build a doomsday weapon that would just, because they hated the Russians. And there's a factor of 4, which is something that's in favor of thermonuclear ignition. It's either a gift of God or the other part. It's either the work of God or the work of the other. But Von started to hedge his bets. So he was building this, very consciously building this device that could destroy all life in the world. And I think to sort of make amends for that, he decided, how about creating life? We're using these computers to destroy all life on Earth. What about, so he brought in this crazy another Italian Norwegian mathematician, Niels Barichelli, who came in and did experiments on creating sort of artificial life forms within the memory of the computer in 1953. And this thing was just, the total memory was 5 kilobytes. There's Barichelli on his application for a Fulbright grant, which was declined because it good for everybody who was Italian or Norwegian. And he had a sense of humor too. It's that easy to create billion dollars of money and create a few yourself. So he's the first person to talk about a digital universe.